Now we are going to look at the eigenvalues and eigenvectors. X is an eigenvector of a matrix A if the multiplications of the AX is a scalar multiple of X. So what does it mean? So which means that when you multiply a matrix A with a matrix X, your final answer is actually a scalar multiplications of the original vector X. So it depends on the magnitude and the signatures or the sign of the eigenvalues here corresponding to X. The operations of AX equals to lambda X actually compresses or stretches the X by a factor. Now here I showed you 4 possibilities of the cases when your lambda value is in between 0 and 1. So when you multiply the XX is the original vector here with the lambda value, your new vector will be shorter than the original one. But if your lambda is larger than 1, so your new vector, the red color here, lambda X, will be longer than the original vector. While in another case, when your lambda value is in between 0 and -1, you'll have a new vector which is in the opposite directions of the original vectors X here, but the magnitude will be shorter. And if your lambda is much lesser than the 0, -1, so you will have a new vector in the opposite directions where the magnitude is longer than the original vector X. Now let's visualize it. So you have a matrix A and you have a vector X and matrix A. When you multiply the A and X here, you get 3 and 6. So this 3 and 6 is actually a 3 multiplications with the original vector X here. So if I'm going to express in the diagram form, so this black color will be 1, 2 is the original vector, and when you multiply it with the matrix A, you'll get 3 and 6. So this will be it. And then this is the example of the multiplications of A and X to show you that the multiplications of A and X is actually a scalar multiplications of the X here. Now we want to know how to find the eigenvalues and eigenvectors. So this is actually their derivations from the AX equals to lambda X, where you move the AX to the other side and you factorize out the X vector here. So this should be the lambda identity minus the A matrix here. So for lambda value to be an eigenvalue of A, so this equation must have non-zero solution for X, because if X is 0, then there's no point, you wouldn't be able to find out the lambda here. And from the equivalence statement, AX equals to 0 has only the trivial solutions. So for this case, the X must not be 0. So the determinant of lambda I minus A here must be 0. And we call this as a characteristics equations of A. So we are going to use these characteristic equations of A to get the values of the eigenvalues. So if you're not familiar or you can't visualize the value of lambda I minus A, I advise you to write it aside. So write it out, lambda I minus A, what is it? And then you substitute into the determinant. So in this example, for the A matrix, we found out that we have 2 eigenvalues, -1 and 3. Now why don't you try to find the eigenvalues for this matrix B, where you should find 3 eigenvalues here. By the way, remember when you deal with a square root, remember to have a plus minus sign here. So one of the tips is that when your matrix is in the form of upper or lower triangular matrix, then your life will be easier. You just need to take the entry along the diagonal, and those values will be your eigenvalues. And of course, the eigenvalues statements will contribute to the equivalence statements. So lambda is an eigenvalues of A, and the system equations lambda I minus A equals X. My equation lambda I minus A multiplied with X vector equals to 0 has a non-trivial solutions, and there is a non-zero vector X such that AX equals to lambda X, because if your X is 0 vector, then there's no meaning, because 0 vector you can multiply with any matrix or any lambda to get the values, and it doesn't contribute anything to our life. So lambda is a solution of the characteristic equations for this. And that's all for this basic introduction of eigenvalues.